Okay, so we have the midterm exam coming up next week. So it's written for about 90 minutes. We'll start at 7. It'll go from 7 to 8:30, okay? And there is lecture afterwards. I'm sorry about that. So if you finish early, you can, I don't know, sit in the back or step out, do whatever you want. Just be quiet. Okay, it's going to be all multiple choice. I will provide the bubble-in forms. And if you would like, I could grade it on the spot as well. But some of you would rather have a little bit of, some of you would rather not know your performance immediately. So, okay, so I could grade on the spot if desired. Okay, so you will see a mix of calculations and calculation problems and a few conceptual ones. Conceptual slash, I don't know, definitions or terminology. Anything covered in the homework is considered fair game. Homework problems. Okay. You will need to bring your reference tables, calculator, photo ID, and you are allowed a note sheet, 8.5 by 11. Okay, notes on one side. Yeah, one-sided. Yes.
What do you mean by notes? Like our card, but
Yeah.
like a half sheet? Oh,
Yeah.
Okay.
Okay. So like your card, and you can put example problems on there if you want, just to guide you. Yes.
When you say that all of the homework is fair game, do you mean the specific problems that you've given us for homework, or like those chapters?
I'm not quite sure if I fully understand your question. So, yeah, I guess anything covered in the problems is fair game, and I mean, the homework problems don't ask you very many conceptual or terminology questions. So I guess you are responsible for some of those things as well. So I mean, for example, I could ask which descriptive statistic is not affected by outliers in the data. And your choices would be the mean, the standard deviation, the median, the variance. And you would tell me which of those descriptive statistics are not affected by outliers. And the answer there is the median, okay? The other ones are affected by outliers, okay? So, I mean, that's not a homework question, but I feel like that we've covered. Yes?
And then it also includes the homework that's due next week too, right?
Yes. So the stuff I covered today will be on the midterm, okay? I'm not covering a whole lot today. I'm just expanding a little bit more on confidence intervals today. So it's not a ton of new material. We'll just do a little bit of review, and then I am assigning another lab in R, and I'm going to, I know you guys hate it, so, but that's not going to be due next week. It's going to be due the week after the midterm, okay? So this week you can focus on studying for the exam. The lab will be due the week after. But because it's kind of related to this stuff, I'm going to cover how to do it in today's lecture, and the video will be recorded, and you can on your own time after the midterm exam you can work on it. All right, is that okay? Yes.
Is the second lab going to build on stuff that we used in the first lab?
I don't know, but I don't know. Some of these questions I'm not sure what the answer is that you're looking for, and I'm not entirely sure how to answer the questions either. So it uses R, so if you've gained some familiarity with R, then that will be useful, but it's a different data set. So yes.
It looks like we have 4 labs in a row. So does that mean we have 2 labs that are the same week, or is it?
I don't think it's 4.
That was going to be my question.
I'm looking at it right now.
Let me see.
We could just get rid of one of them.
Okay, so I got lab 2. So lab 2 will be due May 14th, and then so next week is the midterm, right? So I'm not assigning homework in lab next week. Does that make sense?
Yeah, but I guess based on your syllabus, it says, because we're on homework 5 and lab 2, and then the following week is homework 6 and lab 3, and so on.
I
and so
see.
forth for 4 classes in a row.
So this is how. So homework 5 is technically quote unquote due, right? So you should have completed homework 5 by next week, which is the midterm. And then lab 2, which I'm assigning today, you have 2 weeks to do, is due the week after the midterm. And then the following week, lab 3 will be due. So yes, you do have 4 labs in a row, but no 2 labs due on the same day.
We do though.
We do.
See how it says?
So lab 2 due this day,
Okay.
week 7. Lab 3 is due week 8. Lab 4 is due week 9. Lab 5 is due week 10. So I'm not assigning a new thing on week 6 is what's happening.
So there's going to be no homework on the stuff that we cover next week in lecture, is what you're saying?
Correct. I'm not assigning a new homework assignment. I'm just saying finish up your lab. But worry about that next week, okay? Okay. So that's that. I think the midterm is fair difficulty, okay? It's not super hard, it's not super easy. But of course I would think that, so. Yes, question?
Like the quiz, do you have to know the R, like?
There's probably going to be 1 or 2 questions max out of we're looking at around 40 questions, okay? And they're going to be no harder than the R questions that I put on here. Like, how would you do this computation in R? Okay? Okay. Sure. It's already May. Tomorrow, May 1st. Third of the year. It's already gone. We're already halfway through the 2010s. Close, just as close to I don't know, 2050 as we were to 1980, you know? Or no, 2050 is 35 years away, 1980, 35 years away, so. We'll see what happens. A lot can happen in 35 years, right? The next president, or the president in 35 years might just be a 5-year-old kid right now. Probably 10, but or 30-year-old also. Could be anybody. Probably already, well, required by Constitution to have already been born, so. Okay, well anyway, that doesn't matter. Let's see. Okay, so last week, we're gonna just continue on with confidence intervals. So last week we covered sampling distributions. And the central limit theorem. Does anyone want to step out on a limb and tell us what is the key idea behind the central limit theorem? Yes.
Well, if you have a bigger, it's like trying to get a normal distribution from data that is not necessarily normal.
Correct. So something just happened to my screen. I don't know what happened, but in the central limit theorem, even if our population is not normal, so given any population, as long as we take large samples, large random samples, quote unquote large the distribution of y bar, the sample mean, will follow a normal distribution. Okay? And so this is a key result or key finding that serves as our basis for doing all sorts of future inference. So because we know y bar comes from a normal distribution, we were then able to make confidence intervals. Okay, and so we did confidence intervals. And the idea behind confidence interval is that we observe y bar, and we do not know the population mean mu. Okay? But the central limit theorem tells us that y bar comes from a normal distribution with mean mu. So we know that y bar and mu should not be far apart. Okay. And we already had kind of a basic intuition about this, knowing that the mean of a sample should be somewhat similar to the mean of the population. But the central limit theorem gives mathematical support to that idea. And so, so based on mu, or I'm sorry, so based on y bar, we create an interval or a range of plausible values of mu. Okay, and that range is y bar plus or minus t star times s over the square root of n. So that's what we covered last week. No, that's why. All right, is that okay? All right, so today we will build off of that, okay? And so we will create confidence intervals based on two samples. And it is a we will make we're making a confidence interval for the quantity mu1 minus mu2. Okay, so just imagine we've got population 1. Population 1 has a mean of mu1, and we have population 2 which has a mean of mu2. And the question is, and from population 1, which we cannot observe directly, we draw a sample. And the sample has mean y bar 1. In population 2, we also cannot observe directly, so we draw another sample. And this sample has a mean y bar 2. Now, y bar 1 and y bar 2 will almost never be exactly the same, no matter what our populations are. Even if we took two samples from the same population, y bar 1 and y bar 2 will probably not be exactly the same. So when we take these two samples, y bar 1 and y bar 2 will not have the same value. Okay? But based on y bar 1 and y bar 2, even though they're not the same, could their relative respective populations have the same value? Maybe, maybe not. Okay? So we want to create an interval. So based on y bar 1 and y bar 2, we will make a confidence interval for the difference between the population means. mu1 and mu2. Okay? So it is a confidence interval for mu1 minus mu2. Notice that it is not a confidence interval for mu1 and it's not a confidence interval for mu2. It's not that, it's a confidence interval for the difference. Okay? So again, so the confidence interval goes from a low end to a high end. So just to check our understanding, let's say population 1 is the mean height, the heights of men. Okay, so population 1 is the heights of men. So mu1 would be the mean height of all men, right? Let's just say in the USA. Heights of men in USA. Just so it's... because I'm familiar with that population and I don't know enough about the global heights of all men. Population 2 will be the heights of women in the US. Okay, so what might our what's a possible confidence interval for mu1 minus mu2? What kind of values will we see here?
5 inches.
So are we thinking... Huh? Yeah, okay. So the confidence interval, we're going to have a low to a high. So I would say the confidence interval will probably be somewhere between, 4 to 8 inches, okay? Something around there. This is a possible confidence interval, right? And what does it mean to have a confidence interval for mu1 minus mu2 end up being 4 to 8 inches? So let's say this was the results of a 95% CI. So we took some data, we create confidence intervals. Our 95% confidence interval ends up being 4 to 8 inches. This is a confidence interval for mu1 minus mu2. What is this saying? I would make a statement like, I am 95% confident that something is between 4 and 8 inches.
The differences between the mean heights
Okay. So we'll start off with just we will first take mu1 minus mu2, right? So I'm 95% confident that, so I'm going to just start off here, that mu1 minus mu2 is between 4 and 8 inches. Okay? This is a completely correct and valid interpretation of our confidence interval based on what we have here, but may not be insightful for someone who has not taken statistics, okay? So I'm going to just change this into saying I am 95% confident that ... the mean height of men in the US is between 4 to 8 inches taller than the mean height of women. Okay, so maybe that's a little bit more understandable. So we're not creating a confidence interval for the mean height of men by itself. We're creating a confidence interval for the difference between mean heights. So we're basically saying the average man, if there were such a thing, that the average man in the US has a height that is about 4 to 8 inches taller than the average woman in the US, okay? If there were such a thing. But here we're just saying, or we could just say that the mean height of men in the US is between 4 to 8 inches higher or taller than the mean height of women in the US. So the average height difference between two randomly selected, a randomly selected man and a randomly selected woman would be between, we're 95% confidence. I'm sorry, that's actually not correct at all. Yeah, we're 95% confident that the mean height of men is between 4 to 8 inches taller than the mean height of women in the US. I was going off on something else, that if we've selected two random people, it could be anywhere, right? You could end up getting a really tall man and a really short woman, or a really tall woman and a really short man, and that could be all over the place. But if we were to look at the average height of men and average height of women, we're 95% confident. This is probably based on a small sample. If we took a really large sample, this would probably shrink even further, and it would probably be between 5 to 7 inches. I think it's very close to around 6 inches average height difference between a male and female. 5.5, 6 inches, something around there. Okay. So I started here with the interpretation just because I don't want us to get confused about where we're going, okay? If I asked a question, does our confidence interval provide evidence that the mean height, what's going on here, of men and women are different? What would you say? Okay, and the answer is yes. And why do you say yes?
Because the interval is entirely greater than 0.
Yeah, our entire interval is positive. The interval is, entirely greater than 0. 0 is not between 4 and 8 inches. So we have, based on our confidence interval, we're quite confident that men are taller, that the average height of men is higher than the average height of women. Okay, yes. Basically 0 is not within the interval, it seems clear that the mean height of men is greater than the mean height of women. Okay, so let's get into this. So, or do you need me to go back? Or we're okay. Okay, so we're going to create a confidence interval for mu1 minus mu2 based on 2 samples. And so there are 6 bits of info that we need. 6 statistics needed to solve this. Okay, so from sample 1 and sample 2, we need the size of sample 1, the mean of sample 1, and the standard deviation of sample 1, and we need the same bits of info for sample 2. And your confidence interval will thus be y bar 1 minus y bar 2 plus or minus t star times the standard error. And the standard error, oops, so this is our estimate. Okay, the standard error is just this formula. There's nothing we can really do about it. Some people like to think of it as like I don't know, the hypotenuse of a triangle. And you know, if you have standard error 1 and standard error 2, this is the standard error, the combined standard error, right? So this is S1 over N1, and this is S2 over N2. So some people like to think of it this way. And then so what do you have? You have this squared plus this squared, square root of this squared plus that squared, right? Oops. S1 squared over S1 over square root of N1. So some people think of it this way, but whatever. It just comes down to this is what it is. You don't have to worry about this if you can remember this. All right, so let's try this out. I'm gonna copy this. We'll do an example. All right, so let's do. Oops, what's going on here? All right, so let's say we go to an elementary school. And we take two random samples. I forgot one step, okay. We randomly select 15 boys in 3rd grade and randomly select 20 girls in 3rd grade. Okay, we measure the heights. How tall is a 3rd grade? I have no idea. Let me just check. Growth chart, US, we'll just say growth chart boys and growth chart girls. Okay, let's just see here. Oh my gosh. Okay, 3rd grade is what, 8, 9? 8, stature, 50 inches. Okay. And we'll go something around there. Growth chart girls. Of course it's pink. Oh yeah, right around the same. Okay. Okay, so we measure their heights. Okay. So the mean height of the boys is 50.6 inches with a standard deviation of, we'll say, 2.5 inches. The mean height of the girls, we'll say 50.1 inches with a standard deviation of 2.1 inches. Okay, so I will say make a 95% confidence interval for mu1 minus mu2. Okay. Now I forgot, in selecting your t star, when selecting t star, we will use degrees of freedom equal to n1 plus n2 minus 2. Now this is an approximation. Because the true degrees of freedom is actually rather complicated to calculate. I'll give you guys a minute to figure that out. All right, how are we
We
doing?
always round down, is that?
Yes, if you can't find the exact degrees of freedom, round down. Okay. Are we good? Need another minute? No response. Good. Okay. All right, so I'm just going to list off the data. We got sample 1. And you just have to arbitrarily choose one to be sample 1 and the other to be sample 2. Okay, so we'll say sample 1 was the boys, sample 2 was the girls. If you chose different labels for the sample 1 and sample 2, we'll talk about what happens there, okay? So let's just use that. Okay, so y bar 1 minus y bar 2 will be 50.6 minus 50.1 plus or minus t star times okay, and so to choose our t star, we are going to use degrees of freedom equal to n1 plus n2 minus 2. So that will give me 33 degrees of freedom. So I look here and I don't see 33 degrees of freedom, so I round down and I'm going to use 30 degrees of freedom, and I'm looking for 95% confidence. So I go in this column. 30 degrees of freedom gives me 2.042. Okay, so I'm going to just plug in 2.042 here. And so this is just a matter of punching this. I got 2 instances in our calculator, so I got, so I'm going to do 2.5 squared over 15 plus 2.1 squared over 20. Take the square root of that number. And I'm going to multiply that. Well, I guess just to be on the safe side, I'm going to just say this thing ends up being 0.7982. Okay, I'm going to multiply that by 2.042. And I get 1.62997. So I'm going to just round off to 1.63. And 50.6 minus 50.1 is 0.5. So I have 0.5 plus or minus 1.63. So this goes to, on the low end, I get negative 1.13 inches to positive 2.13 inches. And my interpretation would be, so we are 95% confident that mu1 minus mu2 is between minus 1.13 inches and 2.13 inches. Okay, but let's change this, and I'm going to say we are 95% confident that the mean height of boys in 3rd grade is between 1.13 inches shorter and 2.13 inches taller than the mean height of girls in 3rd grade. Okay. Is the work here okay with everybody? What about the conclusion? That's also okay. So what does this phrasing mean? We're 95% confident that the mean height of boys in 3rd grade is between 1.13 inches shorter and 2.3 inches taller than the mean height of girls in 3rd grade. Do we have, if I said, do we have evidence that there's a height difference between boys and girls in 3rd grade? You would say no. And why would we say no? Because 0 is in our interval. 0 is a plausible value for the difference between the mean height of boys and girls. So 0 is within the interval. Okay? So that means we do not have evidence that mean of boys and mu girls is different. Does that mean they are the same though? Does that mean the mean height of boys and the mean height of girls are the same? Also, no. Okay, so all this doesn't, it's basically, well, we don't have evidence that they're different, but it also doesn't prove that they're the same. Okay, it's just, our samples ended up having slightly different means. It's not enough for us to come to the conclusion that the respective populations have different means, but it also doesn't tell us that the respective populations have the same mean either. It's not an exciting conclusion, but that's actually probably what a lot of statistics research, the conclusions that are made, okay? But they're valid, they're useful, and basically, if you want to make a conclusion one way or another, you basically just have to gather lots more data. Okay, we took a sample of 15 boys and 20 girls. You're not going to be making groundbreaking discoveries with that. Okay? Yes?
Is there anything that we know about this based on the, I guess I'm looking at, it doesn't seem super, there's not a huge difference here, but like say, our interval was much wider, but say it was -5 to 25.
Okay.
Right.
For a height difference?
Well,
or for whatever it is, okay?
Right. Would that tell us, would that give us any reason to believe that it was, that it was more likely that our population mean is above 0, say?
Okay, so if it's like negative, let's say it's just like -1 up to 300 or something like that, okay? Or just something where almost the entire interval is positive, but it just barely crossed into the negative side, or maybe the other way. So yes, that does tell us something, and I would say just lower your confidence level, and that shrinks the interval, right? So if at 95% confidence it crosses, then what you have to say is, if I want to be 95% confident, I can't be sure that there's a difference. But if you're willing to trade off some confidence and say, well, if I make a 90% confidence interval and it shrinks it so that the entire interval is positive, now you can say I'm 90% confident that it's from here to here, you know, +1 to plus whatever, and now I have evidence that there is a difference. The trade-off being you've given up some confidence so that if later on it turns out you were wrong, then you could say, well, to be fair, I was only this % confident, okay? And so there is reasoning behind these conclusions and these statements that we make, because yeah, if you see an interval where it's like almost the entire thing is positive and it's just crossing over into the negative, you part of you wants to say, well, it seems like we have good evidence that it's positive or whatever. And so the technical rule is, if it crosses 0 and it goes into the negative side, you have to say 0 is a plausible value. But if you're willing to give up confidence by shrinking your interval, or if you want to shrink your interval by giving up confidence, then you might be able to make the conclusion that seems to match your intuitive sense. Okay? And that's not being manipulative or trying to lie or anything like that. It's just you should state that you've given up confidence and you've said, and you have this confidence level, or things like that. Okay. And a keen observer might also say, okay, well, your confidence interval barely missed 0, and your confidence level was actually kind of on the low side, so I'm not ready to jump to that conclusion either. And you're going to have people who are honest people who've studied statistics disagree about what the data says, because they might have differing opinions about how these types of situations should be handled. So, okay. So yes, that's a very good point and observation. What would happen if I had labeled the boys sample 2 and the girls sample 1? So if we do this, basically this side of the confidence interval, the plus or minus this 1.63, is unchanged. Okay, if I labeled this sample 2 and this sample 1, I go through all of this, basically I'm just going to switch the positions of this within the square root. That doesn't change the value. So this thing remains unchanged. The only thing that changes would be this goes from 0.5 to negative 0.5, okay? So I'm going to just do this in green. So the only thing that changes here is now this becomes negative 0.5. So if I call this, you know, sample 2, and this is sample 1, this becomes negative 0.5, and then so my interval ends up being negative 2.13 to positive 1.13. That's the only thing that changes. Can we see that? Okay. And so my interpretation would go, we are 95% confident that the mean height of girls in the 3rd grade is between 2.13 inches shorter and 1.13 inches taller than the mean height of boys. Okay, I'm essentially saying the same thing, exact same thing. Or I am saying the same thing. In one, I'm saying, you know, boys are, if we just look at this number 2.13, I'm saying at one end, boys could be 2.13 up to 2.13 inches taller than girls, and on the flip side, I can say on the other end, girls can be up to 2.13 inches shorter than boys. Okay, so it's, you know, tomato tomato. You know, group A has a value larger than group B, this much larger than group B, or group B has a value this much smaller than group A. You're saying the same thing. You're just making a comparison. Okay. All right, let's take a break there, and we'll come back.